YouTube. Testing on YouTube. Testing on YouTube. Testing on YouTube. All right, YouTube is working. Let's go on X. Testing on X. Testing on X. Take a sip of water, spit out this gum. Testing on X. How's it going, Devashish, Mishra, and Sarah? Okay. Should be starting here any second now. All right, I think we're live on X. Let's double check, make sure it works. Testing. Dude, the X live streaming is so janky. All right, it's working. You hire slightly better people to do that. All right. Let's blow this horn and get started. Welcome everybody to another Hoopo stream. Today we're going to be doing an exploration of Gaussian splats for robotics. So we got a lot of papers here. Too many papers. In fact, we're probably not going to be able to get through all of them. But what I'm going to try to do instead is kind of pull out something from each of these papers. So I have probably 10 different papers here on Gaussian splats that all came out recently. You know, everything from Fisheye-Gaussian splats to sliding window video streaming splats to even really weird bespoke things like Gaussian garments. So yeah, rather than going through each of these papers individually, I'm going to try to pull out a little bit of alpha from every single one of these, and then hopefully we can paint kind of a bigger narrative here, which is what is happening with Gaussian splats from the perspective of robotics. What does the kind of future of that look like? Can we expect certain parts of the robot pipeline to be replaced with splats? Maybe what are some advantages of that, some disadvantages, and so on. So that's the mission for the stream today. And as always, you can find all the links and documentation for this here in this repo called Hoopo Docs. And there's some extra stuff in there this week. I made a little Python script here that scrapes using Archive. Archive actually has an API, in case you guys didn't know, but you can search for, given the paper ID, you can get basically the abstract of it. So I scraped all the abstracts for these 10 different papers, and here's the scrape that I got, and then I fed that into OpenAI's O1 model, and then asked OpenAI O1 to tell me what the future of Gaussian splats are. So we'll be looking at that in a second here. Maybe why don't we just go straight into that? So this is what OpenAI's O1 decided is the future of splats given the 10 different papers that we're going to be looking at today. So the efficiency, so aka being able to render Gaussian splats faster, which means you can render them on lower compute edge devices like VR headsets and Robots, dynamic scene handling, so scenes where you have lots of different objects that are coming in and out, longer time spans too. A lot of the Gaussians that we've been seeing up until now are quite short, or Gaussian videos. AI integration, that just seems like a bunch of nonsense. Broad applicability, versatility, different sensors and camera models. So how do you make Gaussian splats work with depth cameras, fisheye cameras, stereo cameras, right? Different types of sensors. You want to make it easy to create Gaussian splats with a variety of different cameras. But I don't know, not particularly great of a summary, but I guess O1 is more of kind of like a programming and math model. So I don't know. I just kind of wanted to see how good it was at kind of summarization. I would almost feel like Gemini is a little bit better at summarization because the Gemini context length is long enough that you can actually feed like the entire paper text rather than just the abstract, which is what O1 can handle. Okay. So let's start with this one. I think this is probably a good starting paper because it really is an end-to-end robotics use case, and they're using Gaussian splat. So this is a paper out of Carnegie Mellon, which is where I went to school. So a little bit of a bias there. You know, I was also at one point a robotics person publishing papers at Carnegie Mellon University. So even though this paper is not necessarily like the most famous research group, I think what they did is pretty cool. So this is called SplatSim, right? So simulation splat as in Gaussian splat. So a Gaussian splat simulation, zero-shot sim-to-real transfer of RGB manipulation policies using Gaussian splatting. So an RGB manipulation policy is effectively just a neural net that takes in an image and performs some kind of manipulation task. So in this case, this is usually called a kind of a push task, where basically you have this little T-shaped object or something else like that, and you're trying to move it to a different position, right? Or I think there's also like some variant of pick and place that they do here where you have to pick up the red apple on the desk, right? So this is a UR robot. I think they actually have the full description of the robot here. UR5 robot equipped with a Robotic gripper. So that's the gripper right here. Then that's the robot arm. 2 Intel RealSense cameras. These are depth cameras. So these cameras will give you an explicit depth, which you can use to initialize these Gaussian splats, which is a trick that pretty much everybody's using now. And then NVIDIA RTX 3080 Ti GPU, which is just a consumer-grade GPU that you have in some Linux PC workstation. So pretty kind of standard manipulation setup here. But what are they using the Gaussian splats for? Right? Like where is that coming in? So let's look at this. Sim-to-real transfer, which is how do you get data that has been collected in simulation? How do you train something in that simulated data and get it to transfer to the real data, right? So if you train a robot entirely in simulation and then deploy it in a real environment, it's not going to work as well, right? So this is called the sim-to-real problem of like, how do you train something in sim, which is very easy to do in the cloud. You can do it in parallel. You can collect a lot more simulation data than real data, but it just isn't quite as good as real data. So how do you deal with this significant domain shift between synthetic and real-world visual data? And this is where they're going to be using Gaussian splats. So they're going to be replacing the traditional mesh representations with Gaussian splats in simulators. Okay, SplatSim produces highly photorealistic synthetic data. Okay, so effectively, here is the figure. And a lot of the papers today, we're mostly going to be looking at the figures because I think in terms of getting alpha from a paper, some of the most alpha you can get is from the figures, right? So like, when I'm looking at a paper that I haven't read, the first thing I do is I read the title, I look at the release date, I look at the organization that has released it, I'll read the abstract, and then I'll scroll to the figures, right? And I'll just read these figures. Kind of, you get a much better idea about what's going on, and these type of figures are some of the most information-dense things you can stare at. So if you can stare at this figure for 5 minutes and then eventually figure out what's going on, that'll give you a much better summary of the paper than trying to read the whole paper like token by token as if you were a language model. So a lot of the stream today is going to focus on the figures. So I apologize for people that listen to this stream like a podcast because it's going to be a little bit different. How's it going, Joss? Nice to see you. am I planning on any stream about Moshi? This is a question by Devashish. I actually ran Moshi yesterday or 2 days ago. So I saw Karpathy tweeted about it. Moshi is basically a speech-to-speech model that you can run locally on your computer, and I was able to run it locally. I actually posted the commands that you can copy-paste on the Discord if you want to test it locally. It's cute, you know, it'll sit there and you can talk, and it knows how to kind of interrupt you, and you can interrupt it. So there's the kind of speech-to-speech, the next generation of speech-to-speech, right? Those capabilities are there, but it's not really intelligent, right? It doesn't really tell you things that are interesting. It kind of just like, it's a speech-to-speech demo for the sake of a speech-to-speech demo. But yeah, maybe we do a stream next week on kind of the current state of multimodal kind of speech-based stuff. But this stream is going to be about vision and 3D representation, specifically Gaussian splats. Okay, so we're starting with this robotics paper here, and the first thing that you have is expert demonstrations in sim, and this is what sim looks like, right? So this is a simulation, and this is a mesh and just a classic PBR, like mesh-based simulation, where every single rigid body has a mesh, which is a bunch of vertices. There's some texture applied to that, and you can control it, right? This is something that was built using Unreal Engine or Unity. This I don't know exactly what simulator they're using here. It's probably somewhere in this paper. But you can control these simulations much like you control a video game, right? So you have some expert in the video game sitting there and controlling the simulated robot, and ultimately you get these trajectories, which are basically like, given this image, I moved this way. Given this image, I moved this way. Given this image, I moved this way, right? And you have like the whole trajectory of like every single action that the user took in order to grab this ball and put it probably in this hole. Okay, you're going to take those, and you're going to use them to basically move a Gaussian splat of the robot scene, right? So you went and you recorded this entire scene with some kind of cell phone or something, right? And you created a full Gaussian splat of this scene. But this is going to be a static splat, right? So you actually don't have any way of kind of controlling that splat. It's just basically the static splat. So unfortunately, they have to do a little bit of hacky stuff here. So in order to get the robot in the splat scene to move, they have to do this kind of hardcore stuff here where they take the different Gaussians that represent the different parts of the robot, and they segment them into the different links, and then they can basically move it as if it was a articulated object within the splat. So not particularly great. You wouldn't want to have to do that for everything that moves in the scene, but the result of that is that you now have a much more photorealistic simulator than you did here, right? And when you take these trajectories in your sim and then basically re-render them in this splat, you now have a bunch of RGB trajectories with expert control actions for every single image. And now you can take your data set, which would have been very difficult for sim to real transfer, and now it's going to work a little bit better for sim to real transfer, right? The diffusion policy, this is the neural net that actually receives the image and then outputs the control action at inference or test time or eval time, whatever you want to call it. And the way diffusion policies work, right, is they start with noise and then they diffuse out the actions that you take, right? So you could largely, the diffusion policy doesn't matter, right? This technique works with any type of policy. Really, the thing that they're doing in this paper that's different is the fact that they're using Gaussian splat renderings. And this is something that we've seen before as well, right? We actually saw this in the DeepMind OP3 robotics paper, right? So the DeepMind OP3 robotics, this one. Learning agile soccer skills for a robotic bipedal robot. All right, I'm not actually going to get the, but for this paper, right? So whenever they did all the training and simulation, they actually used a NeRF to render the background, right? So in the simulation that they use for these robots, the soccer field and the goal and the ball and the robot were all meshes and textures, but they didn't want to just leave the background empty, right? So you see how this background here, the background is a NeRF, right? So why are you using a NeRF or a GSplat? Why is that better than just using meshes and textures, right? Because the problem with meshes and textures is that they're a pain to create, right? And I have here, let's go into this paper because this paper has a nice little summary here of what's going on. Okay, so here you have a comparison of different 3D primitives, right? And Gaussian splats are just one of many different types of 3D primitives. So a NeRF, which is a different type, it's a neural radiance field, delivers high-quality renderings with reasonable storage, blah, blah, blah. Meshes, which is what pretty much every single video game you use right now uses, although relatively compact and rendering friendly, require extensive manual labor to create, especially for high-quality volumetric videos. Okay, so this is the problem with meshes, right? If you were to actually create a simulation of this scene in a photorealistic way so that you could have easy sim-to-real transfer, you would now have to have a 3D artist that creates every single one of these posters and gets every single one of these posters right and gets all the cables right and gets the corners of this table and gets the texture of the table, right? You can see how creating those meshes and textures manually would be extremely difficult, right? You'd have to get an expert human artist and they would have to create this entire scene. It's a hell of a lot easier to just go around, film the entire thing with your iPhone, put that into a Gaussian splat, make a little Gaussian splat from that, and now you can render any arbitrary view, and it's going to be much more photorealistic than something that you could create manually. Maybe not, right? I think there's 3D artists that are pretty good. They could probably create a very realistic-looking simulation of this, but it's significantly easier, and it doesn't require that kind of manual creation process. So that's the same reason why DeepMind used this as well, right? Because having a human artist create the background with the shelves and all this crap, it's kind of a waste of time, right? Just get a NeRF of the entire room and then just use that NeRF, and then now your simulation is much more photorealistic, right? And the advantage is that a NeRF or a Gaussian splat, you can render it from any viewpoint, right? So it's similar to how 1x world models work. Not quite. I think the 1x world model is literally in pixel space, so it's creating actual 2D images. This is like there's a representation of the scene that is the NeRF or the Gaussian splat, and then you can render arbitrary views within that, right? So there is a difference between, hey, here I'm just going to directly predict the 2D image versus like here's a 3D representation of my scene, and I can tell you what arbitrary 2D view from any arbitrary viewpoint is. Okay, so we're going to now sneak peek into this next robotics paper here. This one's called Bayesian Embodied Image Goal Navigation with Gaussian Splatting, where they basically have this little robot blimp. So here's the little robot blimp, right? It moves very slowly. You can kind of control the movement, and it's trying to get to different positions within this map, right? So you have this kind of room that they set up with different columns and different objects, and what it's doing is image nav, which is image goal navigation, where you give it a specific goal image. You're like, here, I want you to go to this place, and it's an image, and then you have the image coming out of the blimp, right? So you need to use visual perception to guide the robot to the location where the target image was originally captured. And very similar to all these other papers, right? They use Gaussian splats for the reason that creating this with meshes and textures in a classic kind of Unity type program is going to be very annoying and difficult, and you need to have a human person create that. So being able to walk through the scene, and they tell you exactly how they did that here, right? So they had someone collect 534 RGB images at a resolution of 1920 by 1440, along with a position and pose during capture using an iPhone with markers attached to an OptiTrack equipped room. So this room has a tracker, which means that you have like basically those little marbles that you see on maybe someone doing motion capture. You can put them on your phone, and there's somebody walked through this entire room with that on their phone, so they know what they know the position of their phone for every single picture that they took, which means that they can just feed all those images with every single one of the phone positions into a Gaussian splatting process, and it learns over time the positions of these little Gaussians, and then you can have now this representation of your entire scene that you can render from any arbitrary viewpoint, right? And that is effectively a huge shortcut, right? Rather than having to create all these meshes and textures to have a simulation and always be dealing with the issue that your simulation is just not quite as good as your real scene, you can now create something that is very, very similar to your like photorealistic, that is very easy to make. All you have to do is just walk through your scene with an iPhone, right? Or any camera, right? It doesn't need to be an iPhone. So both of these papers are effectively leveraging the fact that Gaussian splats produce are much easier to create and produce a much more photorealistic simulation than something that you create by hand. Now, the main problem with both of these, right, and both of these suffer from this, is that you can't change this, right? So the fundamental problem here is that it's a static scene, right? There's nothing changing in the scene. It's like the columns are always in the same place. Everything is in the same place. Once you record this scene and create that Gaussian splat, you're not really changing it, right? So it really only works well within the context of a very static scene, right? Even in this one, right, the only thing that wasn't static in this scene is the robot. So the robot is going to be moving around. So they had to do this hacky stuff here in order to actually get the different Gaussians that are associated with the different parts of the robot to move. So there's still that issue of like, hey, there's a static Gaussian splat model, right? But if you're dealing with a relatively static scene, such as this room here, or the room where this robot is, or the room where this little robot soccer setup is, then it's actually a pretty good hack to use Gaussian splats as the underlying scene primitive, because they produce really photorealistic renderings from any arbitrary viewpoint, right? So at any point in time, you can say, okay, what would it look like if I was standing in this position at this scene? And that is effectively what this paper is doing, is they're basically using image similarity as a criterion for judging whether the robot navigates to a goal or not, right? So they have some image similarity, and ultimately the robot is just kind of using some classic kind of Monte Carlo-based model predictive control. Model predictive control is a type of control where you have a model that can basically predict things. Here, your model is this Gaussian splat that's predicting the viewpoint at every single... You can query it at any point, and it'll give you the image there. Then you can look at that image there and say, how does that compare to the image that I have right now? If the images are close, that must mean I'm close to the goal. If the images are not similar at all, that must mean I'm not close to the goal. So that's pretty much... You can see here, we can actually look into the figure here. So you have your image goal, which is like, hey, I want the blimp to get to this position. Here's your measurement here. That's your current position, right? Then you feed it through this model here, which is just going to basically tell you these images are very different, or these images are not different at all, which means that they're very close. You must be close to the target location. That's going to give you some location within your static scene, and then you can effectively path plan through that, right? N sets of T-length rendered rollouts. A rollout is this idea of the Monte Carlo, right, where you start at a state, you take some action, you get to the next state, and then you say, okay, in that state, what action do I take? And then in the next state, what action do I take? And then in the next state, what action do I take? And a rollout is basically a sequence of these state action, state action, state action, state action. In this case, the states are just images, right? So it's not like a position in some board game, right? That would be the state if you were doing Monte Carlo for like chess or something like that. In this case, they're doing Monte Carlo, but in kind of image space, if you want to think of it that way, which is pretty cool, right? And because they have this static Gaussian splat, they can effectively render any image at any position in this scene, as long as the scene doesn't move. So that's really the big problem with using Gaussian splats as the scene primitive, is that they can't change, right? So that's a problem that I have with both of these papers, but we're going to look at some papers where they actually try to address that issue, right? So those are the two robotics papers, and the TLDR for these robotics papers is that Gaussian splats are very good as scene representations because they're very easy to create for arbitrary complicated scenes. You don't have to manually create all these assets and load them in and randomly do stuff with these assets. And they're quite photorealistic. I think actually in this paper they give you an actual number here. So in a zero-shot manner, which means that you only train with the synthetic simulated data, right? You're only training your diffusion policy with the Gaussian splat renderings. You can get 86% task success, which in this case is like pushing the little T into the desired position or grabbing the apple or whatever little task variant they have here, as compared to 97%, right? So if you were to train on real-world data, your diffusion policy would succeed 97% of the time. If you were to train only on the Gaussian splat synthetic data, your policy is getting 86% of the time. And that doesn't seem huge, right? You're like, okay, well, what the fuck? It seems like it works way better with real world data. And it's like, yes, that is correct, but the whole point of this is that if you can get closer and closer, right, you're closing this sim to real gap. At some point, you can hopefully get a model that transfers zero shot 99% as good as the policy trained on real world data, because really what you want is to not have to collect this real world data, right? This real world data is a pain to collect. If you can just do everything in sim, it'll be much easier. Okay. Gaussian splat looks like a flat Earth. Poor robots. I think this is just a 2D projection, this one here, of the scene, right? Because like the real Gaussian splat is 3D. It's like this, right? So this is what the real Gaussian splat looks like. It's a full 3D volume of space where you have these little Gaussians. And maybe this is a good time to talk about specifically what Gaussian splats are. And I think, so much like any other, like if you read a bunch of reinforcement learning papers, every single reinforcement learning paper is going to have some kind of little section where they describe what a Markov decision process is, right? So in a very same way, every single Gaussian splat paper usually has a kind of a little summary here where they tell you what Gaussian splats are. So out of all these different papers that we're looking at today, I think this one actually has the best kind of summary of what Gaussian splats are. So this is the one that we're going to be looking at. So Gaussian splats is a way of rendering a model into 2D images with a given camera pose. So given a camera pose, I can render any 2D image from this scene. In a 3D Gaussian model, the scene is represented with a set of Gaussian points parameterized by a covariance, a center position, a color, and an opacity. So really what a Gaussian splat is, it's a set or just a collection of these little Gaussians, and each of these little Gaussians has a bunch of parameters associated with it, right? So that's really what you're doing, is you're using the fact that the rendering pipeline for Gaussian splats is fully differentiable in order to take image kind of similarity losses and image reconstruction losses, and then push gradients all the way back into these parameters that represent each of these Gaussians. And then slowly over time, you're kind of moving these little Gaussians around, you're changing the color of them, you're changing the kind of size and the scale and the shape of those, and then over time, they approximate your scene. So, right, like this is kind of what it looks like in practice, right? And you can see how some of these splats are kind of very big, some of them are kind of small, and that's a little bit of an issue, which we'll look at in some other future papers here. But that's largely what you're doing when you're doing a Gaussian splat, right? So given a location X, this thing here, the covariance is further decomposed into a rotation matrix, scaling matrix, which you can kind of interpret as the rotation and spread and scale of these little splats. And then you have some ray R, which will emanate from the camera center to the queried pixel, and ultimately the final color of that pixel is computed by alpha blending this subset with the order of z depth from close to far, right? So this is the rendering process that is differentiable. And there's actually another figure in a paper that I think shows this well. Here you go. So here is a figure in a different paper called Accelerating Gaussian Splatting with Adaptive Radius, where they show you how this rendering actually works, right? So you have a specific camera position, and that specific camera position corresponds to one specific pixel in the two-dimensional image of the novel view that you want to render. And as that ray traverses out, right, it's going to intersect a bunch of these little Gaussians. So in order to get those, you're going to have to sort them from back to front, or from front to back. I think they do them both ways. And you're effectively alpha compositing, which means that the Gaussians that are closer to your camera have a larger color contribution than the ones in the back, right? So if you have a Gaussian in front of you that's very opaque and red, then the pixel is probably going to be red because it kind of the opaqueness opaques out the other Gaussians that are behind it. Okay, but another kind of important part here with Gaussian splats is that the way that these are rendered is usually in tiles. So part of the reason why Gaussian splats are popular is that the rendering is very fast, right? So one reason that they're popular is because it's a fully differentiable pipeline, which means you can push gradients and that you can change or create these using learning approaches. But the other part of it is that it renders very quickly, and it renders very quickly because you're rendering the two-dimensional images in these tiles, and each of these tiles can effectively be done in parallel. So this kind of parallel rendering allows you to very quickly render splats. And I think there's an actual comparison here in this paper right here. So 3D-GS, this is splats, high rendering speed. But let's look at some of these other ones here. So I kind of disagree with this thing here, right? The rendering quality, high, depends. Kind of, I think there's meshes and textures that have very high rendering quality. There's nerfs that have low rendering quality. There's nerfs that are fast at rendering. There's meshes that are fast at rendering, right? If you had a low poly mesh, that would be very fast rendering speed. But in general, this is the overall kind of trade-off that you get for different types of 3D primitives. So Gaussian splats give you high rendering quality at a very high rendering speed with a middle amount of storage. So why is NERF storage lower than Gaussian splats? Because NERFs are basically this idea that you have a multi-layer perceptron that is storing all that information. So in a NERF, all this information here, the covariance, center position, like you're not explicitly storing that. You're implicitly storing that inside the parameters of a multi-layer perceptron. So a NERF is actually the most efficient or compressed form of a 3D representation of a scene. But a Gaussian splat is more explicit because you're literally storing every single one of these little Gaussians, but that also makes it beneficial for things like robotics, right? Because in robotics, you might want to separate out the different parts of the scene, right? You might want to be able to say, okay, well, I want these splats here, the little Gaussians that are part of this red apple, to have some kind of physics-based properties or something like that, right? In fact, what they did here is literally only possible in splats, right? You can do this in splats because you can take and say, okay, I want to segment out the splats that are part of this arm versus the splats that are part of the robot base. I can do that with a splat. I couldn't really do that with a NERF, right? Because there's no such thing as like segmenting out different parts of the NERF because the NERF is just an MLP. It's just all inside the parameters of that MLP. Okay. Where were we? We were here. We were talking about why NERFs and splats have slightly different benefits or pros and cons. But what else do we have in here? Okay, so why is this paper relevant to robotics at all? Well, this paper, SWIN-GS, which stands for Sliding Window Gaussian Splatting, right? So S stands for sliding, WIN stands for window, and then GS stands for Gaussian splatting, is about streaming, right? So how do you stream the scene information to some other computer, right? So eventually, we're going to want to be able to run or do full volumetric video, which means 3D video, on a VR headset, right? But that VR headset has a very small compute package, right? It's an edge device. It doesn't have the type of GPU that your computer sitting on your desk has. It doesn't have the type of GPU that the computer in the cloud has. It has a very small amount of compute locally, right? So if you want to send a giant 3-hour volumetric video, which is what we're going to be want to be doing in the future, you're going to have to stream it in, right? The same way that you stream your video in from Netflix. It's not like Netflix sends you the like 10 gigabyte video and then you download all of it and then you play it. It kind of streams into you chunk by chunk. So in this paper, they're figuring out how to do that with splats, right? How do you stream in splats chunk by chunk? And we can actually skip forward here. This is what's actually happening on the client device GPU. So this would be the actual VR headset, or it could be the robot, right? You can imagine a situation where a robot is navigating a world, and that world exists as a splat in some kind of cloud computer, right? So there's a cloud computer that has the full world and the world as a Gaussian splat, and the robot isn't going to have the full world, right? So it's going to be streaming in that world from some cloud computer, right? So in this situation, the client device GPU would be the actual robot, and then it's streaming in the volumetric video or the splat from the cloud, which has the full world, right? And you can see how really the way to do this efficiently is to basically take Gaussians out and bring Gaussians in, right? Because over the course of this volumetric video, there's going to be, the Gaussians are going to change, right? You're going to be, some Gaussians are going to come in, some Gaussians are going to come out, right? As different things go in and out of the video, maybe the background changes, you're going to have different Gaussians that represent different parts of that thing, and you want those to kind of go in and out of your GPU memory, which is on your local device, right? So you can see here, slices already in GPU for rendering, new slices being loaded, slices received and buffered, not loaded. So very similar to anything else that is streaming based, you're basically receiving new information, and you have to get rid of the old information that you don't need anymore and then put in that new information so that you can render it frame by frame by frame in a very efficient way, right? And okay, one of the things that complicates that is that, for example, in some of the previous, let's go to this paper here. Is this the paper I want? No, I think this is the paper I want. This is the paper I want. This is the paper I want. No, which one is it? I had it pulled up. Nope. Nope. Is it? Okay, I think it's this one. There we go. Okay. So this is a paper, Robust Dual Gaussian Splatting for Immersive Human-centric Volumetric Videos. And in this one, they make very high-quality volumetric videos, which is just a Gaussian splat that has the time dimension, right? So it's like a 3D video where it's not just a static Gaussian splat like you have here, right? This is a static Gaussian splat. This one here, also a static Gaussian splat. So this is a real video Gaussian splat, if you want to think of it that way. But the problem with this one is that every single frame is a different splat, right? Is effectively the problem. I think they say it here. I'm going to try to have to find this. Removing reliance. Once a frame is decoded. Okay, so yeah, every single frame is effectively a new Gaussian splat. So think about how much overhead you're doing there, right? You're, rather than having one Gaussian splat that changes over time, which is what they're doing here, right? In this one, they have effectively like this Gaussian splat where some of the splats are coming in and then some of the splats are going out, right? So you're kind of like removing part of the splat and then adding part of the splat over time, right? So that's how you're getting a volumetric video. It's like you're swapping out Gaussians. In this one, they're not doing that at all, right? In this one, oh, Jesus Christ, I should have organized these. In this one, every single frame is basically a new Gaussian splat, and you have to figure out a way to, okay, if every single frame is going to be a new Gaussian splat, I have to very efficiently encode this Gaussian splat, right? So they have to do this kind of overly engineered shit here that they call the hybrid compression strategy. We compress joint Gaussian motions using residual vector quantization, encode opacity and scaling via codec compression, and represent spherical harmonics with a persistent codebook. Okay, so there's the position, rotation, the scale, the opacity, the spherical harmonics. Those are all different properties of the splats, right? So if you remember, those are all just different parameters that you have for every single one of those splats. What they do in this paper is they basically have a different type of compression for every single one of those that is hard-coded for each of these, right? So it's a very hand-engineered kind of anti-bitter lesson kind of mindset where you're like, okay, what's the best way to compress the position and the rotation? Motion compression. What's the best way to compress the scale and opacity parameters? Codec compression. What's the best way to compress the spherical harmonics? Code books, right? And actually, these are we were literally just talking about residual vector quantization, right? And I actually have that pulled up here. This is a blog post that we were looking at, I think for audio, something audio related. The residual vector quantization is very popular for audio, but it's a way of quantizing or just basically reducing the amount of information that you need to store a data point, right? So like, let's say you have these blue data points, right? Storing the actual position of every single one of these blue data points is going to take a lot of memory, which means that whenever you try to stream that, you're sending it from the cloud to your robot, you don't want to have to send too much information, right? So you have to compress it. So how do we compress it? Well, we're going to create this codebook, right? We're going to discretize our space into these red dots. And then rather than sending the XY position of every single one of these blue dots, we're instead just going to send a single number that says, okay, 1, 2, 3, 4, 5, right? So that single number is much cheaper to send over, much easier to deal with, and your computer requires much less compute to kind of handle. But you've lost a little bit of information, right? Because now, rather than knowing the exact position of this blue dot, you only know that it's near this red dot, right? So, and the code book is basically these 24 possible values, right? So that would be the code book. Residual vector quantization, when you have multiple code books, is now the idea of, okay, I'm going to have one code book that represents basically the precision at this level, and then I'm going to have a second code book that kind of represents the kind of a higher level of precision, right? I'm quantizing the residual, right? The residual is just the difference between these. So the residual is just going to be, I think they have a little picture for this. Yeah, the residual is this pink. So it's just the difference between the blue dot and the red dot, which is what you're compressing it to. So residual vector quantization is, and with multiple code books, is how they are encoding these spherical harmonics. All right, but let's take a step back, because we can get a little bit hypnotized by all the fancy math and all these like very complicated shit that they're showing you here, because ultimately this isn't great, right? Like having 3 different like kind of human designed algorithms for compressing the different properties of the Gaussian so that you can send Gaussians frame by frame, where each frame is a different Gaussian, in order to get something that is high enough quality to render on a single NVIDIA GeForce RTX 3090. Or actually, no, that's what they train it with, but they get this to render on a Pico VR headset, I'm pretty sure, or something like that. Yeah, so this is the Pico VR headset. This is, you could think of it like the Quest headset, but for China, right? So China has a low-cost consumer VR headset, which is this Pico one, and then here in the US, generally we tend to use the Quest headsets. But they're rendering in that in real time on the VR headset, which is very impressive, but in order to do that, they had to do all this very complicated compression, which I think is overkill. I much more like this idea here, where you are kind of taking some Gaussians out and putting some Gaussians in, and I think this is a much better model for a robotics use case, where you can imagine having a huge Gaussian map, right? You can imagine having like a Gaussian splat for the entire building that you're in, right? And you wouldn't want to load that entire building every single time, right? Imagine using this technique to do that. Imagine taking the Gaussian splat that represents your entire building and compressing every single one of those, sending it over to your robot. Your robot has to uncompress all of them, and then it really only renders a little tiny part of that, right? I think it's actually much better to do what they're doing here, where you're kind of only getting the Gaussian splats that are relevant to your particular frame within the video, or in a robotics use case within your particular local environment, right? And okay, so while one thing that kind of is relevant to that popped up in a couple of these papers is this new idea that I hadn't really seen before, right? And this is this idea of transforming the problem into a Markov chain Monte Carlo sampling task. So there's your Markov chains again, right? We were literally just talking about this with OpenAI's O1, where OpenAI's O1 is a model that has been trained to effectively do this planning, right? Where it's doing this Markov chain, it's going out, it's looking in the space of possible token sequences that it can output, and then you have this process reward kind of RL loop on top of that, where you collect a bunch of these reasoning traces. And then for things like math and programming, you can figure out which of those reasoning traces are actually worth it, and then you kind of bake that into the model. So Markov chain, Monte Carlo, kind of appearing everywhere here. And apparently, there's a way to think about Gaussian splatting as Markov chain Monte Carlo, which is kind of cool, right? And this appears in other papers as well. So for example, I mean, this is a little bit of a crazy stream. I'm kind of bouncing forth between a ton of these different papers, so I apologize if it's difficult to follow along, but all right, let me stop for a second here. How's it going? Trust me, bro. Aries and Yatharth. Virtual... Could you link to that blog? Yeah, I'll post the link. If it's not here, I'll add it to it. Or you can just ask on the Discord. You're piecing the story in pretty well. Okay, so we're still investigating this idea of the Markov chain Monte Carlo, which appeared here, right? This is kind of the first. I was like, what the fuck is this? 3D-GS as Markov chain Monte Carlo? What? But here's another paper that also shows that, but I'm going to introduce this paper a little bit briefly. So this is GSplat, an open source library for Gaussian splatting. And why is this paper interesting? So this paper is interesting because it's an open source implementation of Gaussian splats, which is something that was missing for a while, right? So this is the actual repo, and this comes from the Nerf Studio project, which is actually a pretty high quality Nerf repo. So now these guys got together and they made a pretty high quality Gaussian splat repo. And the reason this is very important is because for a while, the implementations of Gaussian splats were kind of all over the place, right? You had the original implementation, you had a bunch of other ones, but there was all these kind of licensing issues. It wasn't perfectly open source, so it always kind of felt sketchy using some Gaussian splat implementation because you were like, this license isn't correct. So we finally got a clean and fast implementation for Gaussian splats that has all the bells and whistles, right? So you can actually go here, and it's not just a Gaussian splat implementation in Python. You can actually go into here, GSplat, and then CUDA, and then into the C source code, and here you go. Here's the actual CUDA code for all the different operations that you have in Gaussian splatting. So rasterizing pixels, right? So here you go, boom. This is the CUDA code for that, right? So this is secretly kind of a huge deal, right? Because before you had to use other people's CUDA code that like wasn't open source, so it was kind of like sketchy whether you could be using it. But now finally we have a full open source implementation with all the CUDA stuff in there, and you can see it's actually sometimes you have to be careful because sometimes the repos that were open source were like made by one person, and one person making a repo is never going to be as good as a kind of a joint effort, and especially a joint effort with these type of backgrounds. So if you look here, you got everything from UC Berkeley, Shanghai Tech University, Amazon, and Luma AI, right? Luma AI is probably one of the, I would say, most far ahead Gaussian splat and Nerf startups. So you have a guy working at Luma AI contributing along with people from Amazon and UC Berkeley, and then even people from China, all contributing together to make an open source implementation of Gaussian splats that you can use to do all your shit. And that's huge, right? And this is, I love Luma Labs for doing this, because a company like Luma, right, has a bunch of internal expertise on Gaussian splats. It could have been very easy for them to basically keep that secret and never release it, right? But the people at Luma were smart enough to be like, hey, if we release an open source implementation of this, it's actually going to benefit us, because the more people that can use and modify and do science with Gaussian splats, the faster this entire field is going to progress. And the faster the field progresses, the more people are going to use Gaussian splats over other types of 3D representations. And the more people use Gaussian splats over other 3D representations, the more our startup is going to grow. Right? So these guys realized what apparently is difficult to realize for a lot of other AI companies, that it's like, you want to open source your shit so that technology just moves faster, and then you're ahead because you're moving fast, right? A lot of companies, they stay ahead by sabotaging the people that come after them, right? Putting patents, keeping stuff secret. But I just feel like that's a bad way of doing research. You want to open source your stuff and then stay ahead by moving faster than everybody else, right? Okay, so that's why I like this GSplat repo. But the reason I want to talk about this, or another reason I brought this up, is because they actually have the same shit as this other one, right? So we saw this here where they were like using, they reinterpreted 3D-GS as Markov chain Monte Carlo. These guys also do that. So MCMC, which is Markov chain Monte Carlo, the blah, 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 adopt an alternative Bayesian perspective to the densification strategy in Gaussian splatting. The authors reformulate Gaussian splatting densification as stochastic gradient Langevin dynamics update. So there you go. There it is. So now we have two different papers that reference, hey, you can actually reinterpret 3D-GS as MCMC and it works better. So I'm like, okay, I got to get to the fucking bottom of this. What is going on? What is this paper? So now let's pull up the paper. This is the one that they're both referencing. This is 3D Gaussian splatting as Markov chain Monte Carlo. Okay. So Gaussian splats rely on the same initialization and densification strategy for placing the Gaussians. Okay, so what the fuck is initialization and densification? So initialization is how do you actually get the original positions for the Gaussian splats, right? So at the very first iteration step, you have to decide where these little Gaussian splats are, right? One way to do that is random initialization of, okay, I'm just going to randomly pick XYZ positions for every single one of these Gaussian splats. Another thing you could do is use ColMap, C-O-L-M-A-P, which is a way of taking a bunch of images, kind of what you would expect from this paper here, right? Like you just have a bunch of images with camera positions, you feed that into ColMap. ColMap will basically give you a rough initialization point for each of the Gaussians, right? It kind of looks at the different images and then uses kind of triangles effectively, just geometry and camera math to figure out, okay, these 2 points are the same point, therefore this point is here in 3D space. You could also use a point cloud, right? So if you have a depth camera, like the Intel RealSense that they have here, you could use the point cloud from that depth camera as the initialization for these Gaussian splats. Okay, so that's the initialization, so which is a little bit in a weird place right now because there's a bunch of different ways of doing it. Another kind of issue is this idea of densification and also pruning, right? Sparsification and densification. So sparsification and densification are the problem of getting rid of Gaussians and adding Gaussians, right? So over the course of your optimization process where you have your set of Gaussians and you're changing the parameters of each Gaussian by pushing gradients, you're going to run into issues where some of these Gaussians become quote-unquote dead, right? So maybe one Gaussian that is kind of floating in the middle of the scene, right? There's nothing near it, so it starts to become less and less opaque over time, right? The opacity of that Gaussian becomes smaller and smaller and smaller and smaller until at some point you just have this Gaussian that is sitting there that is fully see-through and that is basically not contributing at all, right? So I would call that Gaussian dead, right? Where we should just get rid of it, right? And you're going to have the opposite problem where maybe there's a part of your Gaussian splat that has like an empty space, right? So for example here, right? Like the soles of his shoe, there's no Gaussians representing the soles of his shoe. So you'd want to add more Gaussians, right? You want to say, hey, like in this area here, I want to densify or increase the density of Gaussians in this space, right? And there's a lot of different ways of doing that people have come up with, right? So here, Gaussian split vanilla 3D-GS. Here, what they're saying is this is the way that you densify Gaussians in the original paper. So in the original paper, what they do is they'll just take a Gaussian here that's trying to kind of grow a little bit too big and represent too many parts of your scene, and you'll split it into 3 little Gaussians, and then you'll basically optimize each of those little 3 Gaussians, and then that gets you better to your, that gives you ultimately closer to your representation being as picture perfect as possible, right? So this is a densification strategy, right? But what's the problem with that? So these densification strategies, depending on the state of each Gaussian, they are cloned, split, pruned, or aka densified or sparsified, removing Gaussians, the primary way to control the number of Gaussians within the 3D-GS representation. However, this heuristic-based approach requires multiple hyperparameters to be carefully tuned, right? So one of these hyperparameters might be right here, right, where you decide to split this one into 3. Why 3? No reason, we just chose 3, right? So the arbitrary choice of that hyperparameter that you split the Gaussian into 3 is a problem, because now you have this hyperparameter that you have to tune, you have to figure out what the magic value for that hyperparameter is, right? It'd be great if we just didn't have to deal with that. Pruning has a similar kind of issue, right, where whenever you're pruning Gaussians, you also have to kind of have these arbitrary, what they're calling here culling. So in this paper, they call it culling, but it's pruning, culling, sparsification. Those are all the same idea of like, let's remove some of these Gaussians. And you can see here, they actually have this like 500 IQ, like super complicated, like, okay, we're going to cull all the Gaussians that are outside of this bounding box for each Gaussian. And it's okay, but then what's the size of this bounding box, right? So there's some more hyperparameters there. Okay, what's the culling area? So all of these densification and sparsification are introducing these annoying extra hyperparameters that we just rather not have to deal with. So how do we solve this? We're going to solve this by rethinking the set of 3D Gaussians as random samples, more specifically as a Markov chain Monte Carlo samples drawn from an underlying probability distribution. While we assume the underlying distribution, this distribution does not to be explicitly modeled as the Gaussians themselves are already representing it. So distribution is a pretty broad term, right? Like you can think of even something like a diffusion image generation model. What is it really doing? It's learning the distribution of all real images, right? And it learns this mapping function that takes you from random noise to a point on this distribution of all images, right? So even though here they're talking about this idea of drawing from an underlying probability distribution, it's like you don't actually need to write that probability distribution in like some closed mathematical form, right? It's just the Gaussians all together are that probability distribution, right? That's the distribution, is the Gaussians themselves. So any modification to the set of Gaussians can be reformulated as a deterministic state transition, the relocation of Gaussians, where we move our sample, the set of Gaussians, to another sample, another set with a different configuration. Okay, so it might be a little bit confusing exactly what happened here, but this picture makes it very clear, right? So whereas previously we had to do densification and sparsification by using these arbitrary kind of like split or remove based on some threshold where with hyperparameters, now instead what we're thinking is, okay, we instead are relocating the dead Gaussians. So once you have dead Gaussians, we're instead going to be moving them into different positions. So if we ever get a dead Gaussian, we effectively move them into a different. So it's very, ultimately similar things are happening where areas that need more Gaussians to represent things better are ultimately going to get more Gaussians, but now you have the same amount of Gaussians, right? You're just moving your Gaussians around. And that's really important because when you're streaming, you want the total chunk of Gaussians to be the same. For streamable content, maintaining a uniform data volume across time is crucial, right? So what does that mean? It means that the GPU memory, you want it to be full of your Gaussians, which is some specific amount of Gaussians for your specific GPU memory. You don't want that to be like varying over time, right? You don't want to have some frames have 100 Gaussians, some frames have 2 Gaussians, some frames has 10 million Gaussians. Like you don't want to be changing the amount of Gaussians. So this type of strategy where you're instead moving Gaussians around is actually a much better way to ensure that you have always the same block of memory, right? A uniform data volume. Okay. Instead of simply splitting one Gaussian into several, 3D-GS MCMC relocates dead Gaussians to the position of alive Gaussians, those with high opacity and hence high presence in the scene. Okay. So now we have a much better idea of what's going on, right? Where, okay, 3D-GS MCMC is effectively a slightly different way to think about how you do densification and sparsity in Gaussians in order to solve some of these arbitrary hyperparameter problems, and then the fact that you're going to be changing the brick of memory that you have representing the scene as you move it over time, right? But there's still something here that I don't really know what the fuck it is, right? Stochastic gradient Langevin dynamics. Okay, so what is stochastic gradient Langevin dynamics? And I dug deeper, so like I kept going deeper and deeper and deeper into the rabbit hole, and I found a blog post here, a look at SGD from a physicist perspective, part 3, Langevin dynamics and applications. And then there's one section here that made it click in my head, right? So here's Langevin dynamics, and I'm going to read this because I think it's a nice little lead up to the kind of moment where it clicked in my head. So you had this botanist in 1827 who was looking at pollen grains in the water and saw them moving around randomly. A couple of years later, Albert Einstein wrote a paper and said that the motion of these little pollen grains in the water was caused by the random impacts of the molecules on the pollen grain, right? So in 1827, this guy, Robert Brown, basically started this idea of Brownian motion, right? Which is like basically little particles moving around randomly, right? And that becomes kind of the foundation for molecular dynamics, which is the dynamics of little molecules, right? So if you're someone who wants to study the chemistry or the dynamics of like a gas that's moving in a cylinder, right? You're going to be doing this type of Brownian motions math, which is like, okay, each of these little gas molecules is moving around and they can bump into each other and they can cause, there's some dynamics there, right? And there's an equation for that, which is this one here, which is the Langevin equation, which is basically saying, okay, you have the velocity of the little particles, then you have some noise, and that'll tell you ultimately where the little particles are moving, right? So it's basically F equals ma for little particles. So how does this relate all the way back to Gaussian splats? Because what are we talking about here with these Gaussian splats? Well, that's literally what we're talking about, right? We're talking about moving around little dead Gaussians into a different part of the scene. And then that's where it clicked to me. Oh, okay, now I get it. Okay, so it's just Markov chain Monte Carlo in this kind of molecular dynamics space where you have little things moving around and shifting in 3D space, which is literally what we want here, right? We have little things moving around, shifting in 3D space. So that is my explanation of what 3D-GS MCMC is with these Langevin dynamics. Is basically taking molecular dynamics, and I think they actually mentioned it here, where like they came to this conclusion just by noticing that it's the same, right? MCMC draws frameworks. Stochastic gradient Langevin dynamics, which is an MCMC framework. You have the learning rate. You have the loss here. I is an image sampled from the set of training images. So the set of training images would be your this, right? The 534 RGB images that you collected with your iPhone that have some specific position associated with them. And they realized, wait a second, this equation here, which is how you're doing updates for a single Gaussian, is actually very similar. We note the striking similarity between 4 and 5. So all of this shit here, all of this 3D-GS MCMC basically comes from the fact that there was one guy, one of these guys here, probably one of these guys, right, the advisors, who realized, because they probably did some work in molecular dynamics, and they had looked at this equation a lot, they were looking at this Gaussian equation, and they were like, wait a second, that looks very similar to what we do in molecular dynamics. And there you go. And that's basically the kernel of intuition that led to this reframing of Gaussian splats as basically little molecules moving around. And because people have spent a bunch of time thinking about the optimal way to represent these little molecules moving about, they have all this nice fancy math, which is this stochastic gradient Langevin dynamics. And now we can basically apply that to Gaussian splats, which, hey, is going to solve this problem of densification and pruning and sparsity within Gaussian splats, which now means that we can effectively stream more complicated scenes, which allows us to then render scenes that are dynamic rather than static in robotics, which will then ultimately allow us to sim-to-real transfer, which will then ultimately allow us to train things in simulation, which means that ultimately robots work. So that is a very long path of how molecular dynamics research from like 50 years ago is going to basically result in robots that can do crazy shit in the real world despite having never been trained in the real world. All right, let me take a break there. Okay, have I seen Gracia VR? They're going to release Gaussian 3D videos. Yeah. All of these things here are basically, they're all working towards that, right? So if you actually look at a bunch of these papers, like what is the ultimate demo? The ultimate demo is a VR volumetric video, right? That's where we're moving, right? At some point, we're going to have to get rid of the, like a phone is just a shitty intermediate point in our technology, right? We have little two-dimensional screens that we stare at. This thing sucks, right? We want to move to a world where you are in a full immersive volumetric video. You can walk around, like it actually looks like 3D, right? Like that's where we're moving, but we're still in the early days. And ultimately what we can get right now is either like this, which is like a volumetric video of a single kind of asset, but there's a little bit of cheating here, right? The cheating here is that there's nothing coming in, right? It's not like there's a red ball coming in and then this guy like stands up and gets rid of the chair and brings in a new chair. It's like the same guy with the same guitar. Like that's why this paper here doesn't have to do this fancy like Gaussian streaming in and out stuff, is because it's basically always the same video, right? It's the same Gaussians. You're just moving them around a little bit. But a lot of the work that they did was getting this to work on the VR headset, right? So that's really the impressive part of this paper, is that they actually get to a workable demo that renders on a VR headset. But that's also something that they do in this paper. In this paper, they also managed to get this to the point where you can render this using WebGL. And this is the actual demo. So this is the demo of the volumetric video. Let's hit resume here. So you can see here, this is like rendering on my desk or on my computer, right? Using WebGL. And what is WebGL? WebGL is web graphics language. It's quite old now, landed in Chrome in 2011, but there's a kind of a more updated version of this, right? So this is the original WebGL here. This is a 2010 blog post where they're like, hey, you can finally have 3D shit in your browser. Okay. Well, now we have versions of this that actually allow you to use your GPU. So you can use the GPU on your computer through your browser, right? That's fundamentally what you're doing here with this WebGL, OpenGL, is that you want to get to the point where you can use the GPU on your computer to render these Gaussian splats in your browser. And why is that important? It's important because this right here, I'm pretty sure this is not using my GPU, right? This is only using my CPU. But the problem with the CPU is you can't benefit from all of this shit, right? Part of why Gaussian splats are capable of rendering so quickly, right, as they say right here, right, Gaussian splats have a very high render speed. Part of why they can render that quickly is because they do a lot of this, for example, this tile-based rendering. The sort that they use to sort these Gaussians has a particular implementation in CUDA that allows it to be fast. So a lot of the shit that makes nerfs fast requires these CUDA kernels. And if you don't have these CUDA kernels, because you only have a CPU, you're never going to be able to render these things fast enough to compete with the other type of modality. So WebGL and this GPU for the web, which is being worked on by a variety of different organizations here, Apple, Google, Mozilla, Microsoft, and Intel, they're going to effectively create a standard way to render Gaussian splats on any device that has a browser, right? So your VR headset, you can open up a browser on your VR headset and then effectively do this, right? So that open standard will allow us to get to the point where we are watching volumetric videos in the real world or in our VR headsets, and I think that is really the way that we're going to interact with the metaverse and simulated world in the future, right? Right now, everything we're doing is on this little tiny two-dimensional screen. We need to move into this world, right? Do Langevin dynamics have relation with diffusion models too? A little bit, right? Diffusion models are also kind of have this kind of idea of like, hey, you're moving this probability flow, right? So like there's similar stuff there. I think I'm not expert enough on this type of like Brownian motion and kind of like dynamic stuff to tell you the exact difference between what is happening in a diffusion model and what is happening here. But yes, there does seem to be similarity to me between this idea of like moving little particles around in Gaussian splat space and the idea of like, hey, you're at this position in some noise distribution and then moving a little bit closer to the image point in the image distribution, which is ultimately what you're doing in a diffusion model, right? You're going from noise distribution into the image distribution. Okay. Let me go. Okay, the next thing I want to talk about here is maybe one missing piece, right? And there's a missing piece here that we don't have yet in terms of Gaussian splats as the underlying scene representations is the idea of physics, right? So in the original DeepMind paper, right, where they used the nerf to render the background, right, for this photorealistic effect, they didn't use a nerf for the ball and the robot and the pen. Why didn't they use a nerf? Because they actually need to have physics with that ball, right? There's actually some physics here with the ball where this little robot can kick it, right? Which means the little mesh that is the robot's foot is intersecting with the mesh that is the ball, and then you can do some simple F equals ma, and then see how the ball moves, right? So there's all this physics stuff that allows for motion and interaction between objects. That is how it works in video games, right? That physics stuff, the reason that you can drop something in a video game and it lands on the ground, people have been working on that type of stuff for a while for these mesh-based representations, but we really don't have a version of that for splats yet, right? There is the beginnings of it, right? I think we've looked at other papers where people are starting to say, okay, the same way that I have the properties of Gaussians, such as the covariance, the center position, the color and opacity, it'd be great if we started to have kind of physics-based properties such as the weight of a Gaussian, right? The friction coefficient of a Gaussian, the deformability or elasticity of the Gaussian, so you can like have squishier objects and non-squishier objects, right? So we want to get to the point where there's also the ability to more interactively deal with these scene representations, because right now there is no interaction, right? Like in this demo, you can't touch or move or drop any of these things, right? It's not like you can take this guy and grab the guitar Gaussians, right? Or like drop it and it like bounces, or, you know what I'm saying? There's no physics here. So one paper that I thought that was interesting, that was kind of moving in that direction, is this one here, Gaussian Garments, Reconstructing Simulation-Ready Clothing with Photorealistic Appearance from Multi-View Video. And in this one, they actually, it's a little bit complicated because they have a bunch of other shit that they're doing here, which is probably not super important, but ultimately they basically put little Gaussians at each of the points in a texture, right? So they have some mesh texture representation where here's your actual mesh texture, right? There's little vertices, and then they initialize the Gaussians to each of the little points in that. Reconstructing realistic simulation-ready garment assets from multi-view videos, a combination of a 3D mesh and a Gaussian texture that encodes both the color and the high-frequency surface details. But the more important part is this part here, where they have this idea of a physical energies. So not only are you trying to get the appearance of the little Gaussian that is stuck on the stuck on the vertices of this mesh, but you also have this idea of like, hey, we're going to look at the dynamics between these little Gaussians, right? So like if the Gaussians have some kind of bending energy, right? Like if you have two little Gaussians that are next to each other that are part of a stretchy t-shirt, if they start pulling apart, as they pull apart further, you would want there to be something that kind of forces them to not pull apart, right? So you're starting to add kind of these physics properties between Gaussians that are dependent on what object you're actually trying to represent, right? So some t-shirts are more bouncy, some t-shirts are a little bit more like flappy. I don't know how to describe different types of clothing, but you can see here they're starting to add these kind of physics-based kind of relationships between these little Gaussians that allows you to ultimately get to the point where we can hopefully have not just like a volumetric video, but like an interactive volumetric video where you can like literally like push into things and like touch it with your hands, and and then once you have that, then we're cooking, right? Because then imagine this paper here, but you don't have to do this shit because the Gaussians that are part of the robot arm are literally moving with whatever rigid body transformations you want. And the Gaussians that are part of the apple and that are part of the gripper, they're literally interacting, right? So like in the simulator, you're rather than doing what you're doing now, which is there's some mesh and there's some collision and there's some classic kind of physics, like the type of physics you would see in Unreal Engine or Unity, we want to move to a world where the entire scene is all Gaussian based. Even all the physics is all Gaussian based. So, okay. What else? One thing, maybe while I'm talking here, I like this part of the paper where they basically are starting to introduce this physics part, but the one part of this paper that I don't like is that they start from like very complicated things here, right? So this is recorded with this kind of multi-camera setup, right? And I think this one does it even more, where they create this Gaussian face asset, which they call the Gauss face asset, but they start from PBR facial assets, right? And PBR is just a fancy way of saying the mesh texture stuff that I talk about all the time. physically based rendering, PBR. Physically based basically means that you're actually calculating light rays and bouncing and the way that the light scatters from certain materials. It's a digital representation of a human face optimized for rendering using physically accurate lighting, which is basically lighting that actually you're projecting rays and bouncing, and shading process. Mesh neural geometry, image textures include the diffusion map, normal and specular map, and expression blend shapes B. Okay, so unfortunately, in this paper, they have 143 facial assets under 134 lighting conditions with a total of 1,023 combinations. So they already have texture or meshes with the 3 different types of textures, right? You have the actual specular, I think it is, and then you have the normal map, and then the depth. I think those are the name of those 3. But they take those, and then effectively they make a Gaussian for that, right? So it's kind of like a chicken and egg problem here, where like, hey, they have this fancy Go face asset which you can render quickly, right? But here, for example, 110K Gaussian points, achieving 500 plus frames per second on an NVIDIA RTX 4080 GPU. So 500 FPS rendering this Gaussian face asset. But the problem is that in order to create this Gaussian face asset, they used a data set of PBR faces. So I call this the chicken and egg problem, because it's like, hey, well, if you already had these PBR facial assets, why didn't you just use those? So, and ultimately, the reason they didn't use those is because these are very expensive to render. So really, the TLDR of this entire paper is, hey, we have a bunch of very high-quality mesh texture faces. We're going to create this method of like distilling that into these Gaussian splats. And then because they're now Gaussian splats, we can render them very quickly on some limited edge device, such as a phone or a PC or a VR headset. So I don't know about this, right? I feel like this is kind of like a 2024 kind of like thing, because in 2024 it's very easy to create these PBR faces. So now you're just kind of, I don't know. It kind of seems convoluted to me to create PBR faces to then create Gaussians to render quickly. At some point, we're just going to go straight to Gaussians, right? So very complicated. And this one's kind of similar too. They basically start from a very expensive multi-view data set of this person with the clothing, right? At some point, you don't want to have to record like this person in this very specific place with 400 different cameras looking at them in order to create this clothing. There needs to be a way to create this clothing without having the initial starting point. That's my problem with these 2 papers, is they start from these kind of overly complicated setups that nobody has, right? You want to get to the point where it's kind of like this one, where you can create a physics-enabled Gaussian splat clothing from a iPhone video, right? That's not what they're doing here. Here they have the multi-view, like these giant setups. I think they describe one of them right here. Yeah, 81 Z-Cam cinema cameras so like, look at this, like Z-Cam cameras. Like, these are expensive. You know what I'm saying? Like, these are $900 cameras, and they have 81 of them. So, like, nobody's going to be able to replicate this, right? You can't. The whole point of, or not the whole point, but we want to get to a point where you can create volumetric videos from a single monocular iPhone camera. And even in this one, there's a little bit of cheating, because in this one, it's a single iPhone camera, but you have this OptiTrack equipped room. So you have like a perfect knowledge of where the phone is, right? But, okay. To enable high fidelity dynamic rendering, we develop a companion rendering application based on Vulkan. Vulkan is basically they mention it here as well, this one, Vulkan. It's like, just think of it like CUDA, but like open source CUDA. Okay. If I have to shoot a character in a Gaussian splat that requires thinking from scratch, just like how it used to be in the early game dev physics days. I'm not exactly sure what you're asking, Sleepyhead, but yeah, right. there's still a lot missing, right? Because whenever you're making video games, right, there's a lot of interactions that are kind of hard-coded, right? Like, for example, in this type of simulation, there's probably not collision meshes for the robot arm, right? So like a human engineer who is good at these type of simulations, right? So some kind of Unity game developer, they decided, okay, we're only going to have collision meshes for the gripper paddles, and then we're going to have a collision mesh for the ball, and then we're going to have a collision mesh for the actual table, and then there's specific friction properties for each of those that are hard-coded. So, and then I'm going to have some game code and game logic that says, okay, whenever this ball touches this circle here, then I'm going to reset the scene. So there's all kinds of like object-specific logic that's in here that, like, I haven't seen anything in Gaussian splats that's related to that, right? We're still even at the point in Gaussian splats where we're just starting to get to the idea of, hey, let's have an entirely Gaussian splat-based scene where the physics is also using the Gaussian splats. Like, even that is still kind of not production level yet. Can they make sure that this setup satisfies the conservation and constitutive equation? I'm not sure what that means, but you're talking about this setup here where you basically want to make sure that you always have the same number of Gaussians, right? Where you're reallocating the dead Gaussians. So by reallocating the dead Gaussians, you effectively guarantee the same amount of Gaussians are being rendered every time so that you can effectively maximize the memory that you have available on your edge device. Is there papers that use one image to generate a Gaussian representation? Not really. I think that we're still kind of, maybe some of you might know of a paper that tries to do that, but none of these papers are using a single frame, right? And this one here, they recorded the entire scene with many different frames, and that's how they create the splat for it, right? And this one here, same thing. They walk all the way around it with the iPhone, collect 500 images, and then use that to make the splat. In this one here, they also have a multi-camera setup, right? So like right now, you definitely need multi-camera setups to create these splats, either multiple cameras that are all recording at the same time, or one camera that is static, that is moving across a scene. And then the problem with the one camera is that now the scene needs to be static, because you're basically saying, okay, the scene doesn't move, and then I'm going to move the camera, right? And I'm getting the structure from the motion of the camera itself. But if you're doing a dynamic scene like this, right, where this scene is changing, if you tried to just record this with a single camera that moved, then you would just basically get nonsense, right? You need multiple cameras in order to have like a volumetric video or like a Gaussian splat that has this kind of time dimension to it. Okay, I hope that answers your question, Patrick. Let's see what else we have here. We talked about this. We talked about that. We talked about the blimp robot. Blimp robot navigating, doing path planning using image similarity. Here's your policy, right? Your policy picks actions based on inputs. Here's your motion model, which allows you to roll out trajectories, right? And the reason you can do that is because for every single one of these points, you can just go to your Gaussian splat and say, what does it look like to be here? 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 And then because it's a Gaussian splat, it's actually quite photorealistic. Image goal navigation. Image goal, camera image. So you can see these two are very similar, so the image similarity is probably going to be very close, which means that you've basically gotten to your goal. Fisheye-GS, yeah, I guess we didn't talk about this one. So this is kind of like a cool little paper that basically, whenever you create these Gaussian splats, you have the position of these splats relative to the camera, and then you have a bunch of images. But fisheye cameras are actually kind of used in robotics a lot. Maybe not a lot, but they're great in robotics because they can give you a much wider field of view. So you can see a fisheye camera will give you a lot more information, right? Because it can see a lot more things. But it's kind of annoying to use fisheye cameras because you have to basically you have to like rectify them or like kind of like warp them to get rid of this like weird like kind of like fisheye effect. So in this paper, they basically figure out how to take images that are coming from a fisheye camera and use them as the images that you would use to then train a Gaussian splat. 6 indoor scenes. Here's the call map structure from motion, which is how you get the position of the cameras. But yeah, there's not really much to this paper. This paper, anyways. It's literally just how to correct for fisheye effects in order to get Gaussian splats from fisheye cameras. This paper was, I feel like, the coolest one. Also because they just had really nice figures. You know, like, I'm a sucker for good figures. Right? And they also had this little demo, which is pretty cool. Like, look at that. That is so good. Right? Like, imagine doing this with meshes and textures. Like, cloth deformation in mesh texture representations is, like, extremely complicated. You know what I'm saying? Like, getting a t-shirt to, like, deform and, like that type of shit with a mesh and a texture, there's ways of doing it, you know, like, there's video games where you have, like, a cape that can, like, move and deform like that, but it's fucking complicated. There's a lot, it starts to look a lot like this type of shit, you know what I'm saying? Like, just extremely over-engineered pipelines, and I feel like Gaussian splats are just such a simple primitive that I just feel like it's ultimately a way better solution. So when I think about the future where we're all just kind of sitting there in these VR headsets exploring these virtual volumetric worlds, I just feel like Gaussian splats is the perfect primitive for that. And all these papers are kind of pointing in that direction. Sliding window with space-time Gaussian. So, yeah, another thing in this paper that this is the one where they have the Markov chain Monte Carlo to basically reassign dead Gaussians. So they have, unfortunately, they have a bunch of like extra hyperparameters here. You know, like they have to deal with now like the size of this sliding window and this idea of like a lifetime. You know, where like some Gaussian splats exist for this particular amount of time and then they disappear. On one hand, that's a good thing because it means that like, hey, if this person suddenly like grabbed a hat and then put it on, right now you could have a bunch of Gaussians that represent that hat, like before they don't exist and now they exist, right? Or I guess they get reassigned because they're dead, or the Gaussians get reassigned. But yeah, I don't like the just like all the different hyperparameters here. Yeah, let's see if we can have numbers for these. GS, matured, stream, swing size, num.gs, relocate period, iterations. These are all hyperparameters here. Subsequent slices will be received, processed, and buffered by the client. Those slices will be inserted into the GPU memory, replacing expired slices. Right? This is what I think goes beyond just volumetric video and starts to make a lot of sense for a robot, especially a robot that's moving around in a world like this, right? This world is small enough that you can just have the entire world be represented by a static splat. But if you want to do a robot that's navigating like a real environment, especially a changing environment, this idea of kind of like retiring or maturing Gaussians and then putting in new Gaussians, like that's, I think, a really good abstraction to have. There's WebGL. In this one, they initialize from Colmap, which is, I think, probably the most popular way to initialize Gaussian splats. Here's some artifacts due to oversized swing size. So this is kind of what right, we're talking about. One of the problems is these not just with Gaussian splats, but any type of learning approach, if you have, or any type of engineering approach, the more hyperparameters, the more annoying, because for some values of those hyperparameters, it might not work well. So here, for example, swin size, which is one of these hyperparameters here, which is the size of that window, if you choose 4, then it's good. If you choose 16, then you get these errors, right? So like you have to pick the right number for this swin size. And the only way to really know that number is to basically experimentally try different values of it. Got some nice figures. Little WebGL render. Here's the background about WebGL. WebGL features such as compute shaders, algorithms that can add more dynamic details, simulate physical phenomenons, and more. Okay. Faster ML inference. That's another thing with a web GPU, is that you can eventually get to the point where you can perform neural net inferences on your GPU in a browser, right? Being able to access your GPU from the browser is like a huge win, I think. This is the GSplat, which is actually a pretty great, like if you're interested in Gaussian splats at like a fundamental level, like if you really want to know exactly what all the different operations in Gaussian splats are, this is the paper for you, because this is literally like they do it all from scratch. And the reason they do it from scratch is that they don't want any of the legacy stuff, right? They really want this Apache 2 license. They say, hey, there needs to be a publicly available, openly licensed implementation of Gaussian splats from scratch with all the CUDA shit. So this paper is literally every single part that you need, right? Like this is all the equations for the gradients, all the equations for depth compositing, all the equations for the Jacobi. So like they went through and they made this from scratch. They're like, let's do all the math. We'll write it all down. Let's do all the CUDA kernels. We'll write it all down, and then we'll release it. And here's actually the forward and backward computation graph of the main GSplat. So the computation graph is like what is actually... like whenever you take your TensorFlow or your PyTorch code, you write it in PyTorch, and then ultimately it's compiled into this computational graph. That's actually what is being used to get the forward and backward passes. So forward is doing inference, right? You're feeding something in and then produces something, and then backward is like getting the gradients and doing that chain rule and going all the way back to the original properties of the Gaussians, right? You have your center, or this is the position of the Gaussians. You have your opacity of the Gaussians, right? Here's your Jacobians, which go backwards. Now you have your rotation and your scale matrices, right? And then here's your loss, right? So your loss function, which is saying, okay, image A, which is the real image that I recorded with my iPhone, and then this is the image that I rendered when I went the forward. So forward pass, you're taking all this shit here, you're going all the way up here, and you get an image. Then you take some reconstruction loss between those images. This is the equation to actually create the final color of the Gaussian. So you can see here the gradient, the first kind of place that the gradient goes is into the colors, which is why the colors kind of, I guess, change faster. But you can see here it takes a little bit longer to go all the way down into the position of the Gaussians and the opacity of the Gaussians. But yeah, this paper's pretty good. I would recommend it if you're interested in Gaussians at a fundamental level. Okay. Then we have the Markov chain Monte Carlo, which I thought was pretty cool. I still don't really fully understand stochastic gradient Langevin dynamics, but this is enough of a high-level understanding for me that it basically comes from Brownian motion and molecular dynamics, which basically comes from moving little balls around. That's it. Exclamation mark. If you have an ML background, take a little time to look at this equation. Remember what we started saying, that energies in physics and loss functions in ML are analogous. Does the equation above feel a little familiar? Yup, that's a gradient descent update with an added random term. So really a lot of these... which is part of the problem with math, right? Just in general, is that like math is kind of like overly jargonized, if that's even a correct phrase, is that like people put their name on all these different types of things, right? Like Brownian motion is because this guy Brown, and then some other guy called Langevin also wanted to put his name into a thing, and then some other guy wanted to put his name onto a thing. So you start reading some of this shit, and it's like, holy shit, like there's like 10 different terms here, but like half of those terms are just like some guy's name, which is like the guy who created that, and really the underlying kind of thing is actually very similar to other things. So really the variance in the math terminology is actually not representative of the true variance of like actual math, right? Like there's really just a limited set of mathematical concepts, and it's just that different people have been dealing with those same mathematical concepts, looking at them from different points of view and assigning their own terminology and their own names to those things. So math has kind of almost become this kind of like historical field where you're just like, hey, like I'm just memorizing a bunch of people's ways of interpreting things rather than realizing that all of these different things are all really the same thing. I don't know. Sometimes that annoys me. All right, AdR-Gaussian, accelerating Gaussian splatting with adaptive radius. Yeah, this is the one that was kind of a little bit... Rasterization pipeline still suffers from unnecessary overhead resulting from avoidable serial Gaussian culling and uneven load due to the distinct number of Gaussians rendered across pixels. So avoidable serial Gaussian culling, that's actually also got rid of in this one here, right? Because the whole point here is that you don't have to do this culling and densification, right? You can basically think of it like you're just moving the Gaussians around. Uneven load due to the distinct numbers of Gaussians rendered across pixels. What they're talking about here is that when you're rendering a two-dimensional image from a novel viewpoint, right, and you're breaking down your image into these tiles so that you can do each of the tiles independently, some of those tiles are going to have a lot more Gaussians, right? So like, for example, in here, like the tile right here has way more Gaussians than the tile in this corner here, right? The tile in this corner has 0 Gaussians. So anytime you have a parallel process like that, where you're doing things in parallel, you're only as fast as the slowest thing. So even if you can do these two fast, you're still going to be waiting for this one here because that one is going to be the slowest one. So in this one, they do this load balancing somehow to basically ensure that you don't have too many Gaussians in one particular tile. Yeah, I don't like this adaptive radius crap. This just seems like more over-engineered, like hyperparameter bullshit. This paper, this one was cool just because the demo is kind of cool. And they put a bunch of money into it. You know, they have very fancy cinema cameras. They paid for professional artists or professional musicians to come and record. So, like, this is some big money Gaussian splat research. But the problem with big money Gaussian splat research is that you generally can create this kind of like over-engineered solution. And I really think that this paper is like very over-engineered, like having 3 different types of compression for different Gaussian parameters. Like, yeah, ultimately you get a pretty cool result, which is like this kind of like real-time rendering on a relatively small amount of edge compute. But like no one's going to fucking use this. You know what I'm saying? Like this is way too complicated. Residual vector quantization. This one also kind of over-engineered, overly complicated. I also don't like the fact that they start from PBR facial assets in order to create these Gaussian assets. But these guys have pretty good figures, you know? Like the thing about these like papers that have like 50 people on them is that like they always have very nice figures because there's always at least one person that's spending all their time just making the prettiest possible figure. So you can see here how this face is basically, here it's the mesh, right? And then here is the actual Gaussians. They look like little circles. But like, look at all this shit, dude. Pixel aligned sampling and deferred pruning. Like, dude, what the fuck? Imagine the code base for this. Like, imagine how complicated this code base is. It's basically like impossible to reproduce. So what's the point of doing research that's impossible to reproduce? I guess getting 500 plus FPS, which is insane. Similar performance on a MetaQuest Pro VR. Like, think about that. Think about right now, if you have a Quest VR headset, right? The max that can render is like 120 FPS. So And all the stuff that you're rendering on these VR headsets is usually extremely optimized, right? So like whenever you're playing a game such as Beat Saber, right? Like there's a lot of design and effort that went into making it the least amount of textures and meshes possible, right? Because when you're still using meshes and textures to render your Beat Saber. So imagine if every single note was a different color, right? If you had a background that had all these different, that would be more annoying. So like you have to drastically simplify, have low poly meshes for everything, have this kind of distance-based rendering. Like there's so many tricks that go into being able to render your meshes and textures efficiently on a VR headset right now. And Gaussian splats just inherently are much faster to render. So that's why I feel like Gaussian splats and VR just go so well together, because it's going to solve all this like unnecessary optimization that needs to happen whenever you're designing games and experiences for VR, which is similar to what happened in the very early days of gaming, right? Where like back in the John Carmack days, when you were making a game like Doom, like 90% of the effort was figuring out how to like reduce the amount of different things, the amount of different textures, like how to get everything to render fast enough on the tiny little compute budget of like the consoles and the PCs of like the 90s and the 2000s, right? So there's a similar kind of situation right now in VR where like there's just so much effort being put into make things low poly versions, like make it so that you can render it reasonably fast. And I feel like Gaussian splats kind of solve a lot of those issues just inherently by being a better 3D representation. Then there was this one, reconstructing simulation-ready clothing. Yeah, I thought this was a little over-engineered as well, but, you know. Oh, this is another thing. So this is almost completely unrelated, so sorry, guys, but if you are interested in Gaussian splat, so, you know, I'm a Gaussian splats hobbyist. You know, I'm a Gaussian splat enjoyer, but if you're really trying to get deep into Gaussian splats, there's a new technical podcast that came out called View Dependent. This is done by the Mr. Nerf guy, who's probably the go-to, like, he's my source of Gaussian splat papers. So pretty much all these papers come from this guy. But if you're interested in kind of like a deep dive, definitely check this out. Like this guy, he goes and he talks to like the different people that actually wrote the papers. So if you want like a kind of a deeper dive into different Gaussian splat and Nerf papers, I would recommend that. And then this paper. Oh yeah, this one. Okay, so in this paper, they basically have what they call marbles. So really what they're trying to say is that isotropic Gaussian marbles, reducing the degrees of freedom of each Gaussian and constraining the optimization to focus on motion and appearance over local shape. So in this paper, what they do is that one of the problems with these Gaussians right now is that you see how this is a big Gaussian and that you have different orientations here, right? Like in here, you see how every single Gaussian is kind of like a different shape and oriented differently, different scale. Every single one of those is a parameter that you're pushing gradients into, right? So in this paper, what they said is like, hey, what if we just made it simpler? What if we have isotropic Gaussian marbles, which is just isotropic basically means it's the same no matter where you look at it from. And that's really just a fancy way of saying that rather than having these like little spreadable different shaped Gaussians, every single one of them is the same. It's just like a little circle. It's a little ball, a little marble, right? So they're saying, hey, if we get rid of some of these Gaussian parameters here that like account for some of these more weird shapes, and we just simplify it all into these little balls or Gaussian marbles, then we can basically render it faster. So you can see here 200 FPS for Gaussian marbles versus whatever 82 FPS for 4D Gaussians, which has the full kind of anisotropic Gaussians. But that's basically it, guys. That's my cursory overview of the current state of Gaussian splats and what it means for robots. Let me answer some questions. I'll sip some water and then we'll end it. Maybe not a full summary because I feel like I just did a full summary there. How are they going to get to the point where you need an iPhone to make a Gaussian splat of clothing? Is it going to be a foundational model? Kind of. You know, I feel like there's already like a Duster, right? That's a paper that we read before, and that's using a pre-trained transformer to kind of get a little bit of that information. Because these foundation models, like these pre-trained image encoders and pre-trained diffusion models, there's a lot of intelligence inside those pre-trained weights. So works like Duster are basically trying to leverage that pre-training from the foundation models to improve and Gaussian splats, especially just reduce the total amount of images you need and the initialization you need. Like, so I think there are ways to use foundation models to improve Gaussian splats, but we're still just early days for that. I just heard someone calling diffusion as GD, gradient descent and diffusion. I don't know what you mean by that. I'm not well read on meshes, but they're an assembly of triangles. And the Gaussian splat is like the Gaussian. Yeah, meshes are basically... What's a good picture of a mesh? Actually, this one is the perfect. Right? Meshes are this, right? You have a bunch of vertices that are all connected together, so you have to store effectively the connectivity between each of these, right? And then you also have to store the texture. So there's some underlying texture like this, right? This image here, this is like a PNG or a JPEG, right? And this two-dimensional image is wrapped via UV unwrapping, this thing here, UV mapping, into the actual texture like this, right? So that's a lot more complicated than splats. Splats are just there's no order here. It's a set, right? A set basically means an unordered list. Like, it doesn't matter what order these are in. And each of these has a little color and opacity itself, right? So you're basically getting rid of this mesh with all this kind of complicated connectivity and this complicated textures, which are separate files, and you're simplifying it into this unordered set of little tiny splats that you can just, that each of them encode that information in there. Gaussians are good at clothes. I don't know if they're specifically good at clothes. I think that in this paper, they just like, you know, made deformable clothing just because it's novel. You know, a lot of times with these papers, what you're chasing is novelty. So like, you're doing something a little bit weird because it's weird, right? So like the whole, like half of these papers, it's not like this is necessary. Like, it's not like Gaussian splats is like the best way to do clothing. It's just that nobody else has a clothing paper. So if we publish a clothing paper, then we're the only Gaussian clothing paper. So anytime anybody does something, they reference us, right? So it's like novelty is part of the optimization when you're choosing what to research. So I don't know. I don't think Gaussian splats are the go-to clothing thing, but I just think that they're a better representation for deformable objects than meshes. Are the Gaussian splats searchable? Yeah, you could do, so like there's a Langsplat. I think we reviewed this paper, but this is the idea of adding kind of semantic properties to the Gaussians, right? So like as we were seeing before here, right? Each of these Gaussians has these properties, and in the simplest way, they're just color, position, the opacity, right? And you can push the gradients down into that. But you can also add a little vector to each Gaussian, which is effectively like the semantic, like what is this, right? So in this paper, they basically do that. They have like Gaussian splats that are, each splat also has like a little information, which is telling you what it belongs to, right? So like it's a way of kind of adding, in this case, they're just doing it for segmentation, but like you can imagine this type of information would be extremely useful for a robotics use case, right? This type of like semantic information that is tied to every single part of every single object. So you could do open vocabulary 3D query, right? So you could say, okay, I want the chopsticks, and then boom, there you go. That's the chopsticks. Question from GeekoBand. Does it make sense for research to also focus to rendering more complex materials like dielectrics and conductors. I don't know what a conductor is. GS is realistic, but it fails sometimes to render them correctly. Yeah, so, I mean, there's a lot, like, even meshes and textures fail for, like, hair, you know what I'm saying? Like, for example, in this paper here, what's something that you notice? No hair. No hair on any of these, right? So, yeah, there's a long tail of weird things like see-through glass and smoke and hair where Gaussian splats are still not particularly great at that either, right? Like, I guess for hair, you can imagine like a situation where if we get better and better compute, eventually we get to the point where Gaussian splats might actually be the perfect 3D representation for hair, because you could have like a little string of Gaussian splats for every single hair strand. And maybe even smoke, you can imagine like little Gaussian splats that represent the whole smoke. Like smoke right now for meshes, how would you represent smoke in a mesh and texture situation? It's much more difficult to envision what that looks like than Gaussian splats. So I do think that some of these more tricky kind of things like smoke and see-through objects and glass, even though Gaussian splats are still kind of having a rough time representing that, I feel like they're fundamentally probably going to have a less hard time representing that than meshes and textures. How is motion applied to the Gaussian splats? So, I mean, there's different ways of applying the motion. For example, in this one, there's this position and rotation. So every single one of the little Gaussians can move around. I think there's some dynamics to it. Let me see. Basically, like, because Gaussian splats can have an arbitrary values for these little things, right? You can add more of these, right? You can add velocity. You can add like any property that you want. You can add it to your Gaussian splat. So any kind of motion parameter like velocity, you could add it there and optimize. Question from Eunice. It seems like GS or 3D reconstruction is still a luxury for robots, given it's more like a simulation for visual outcome, like expensive rendering, more suitable for game. I wouldn't say it's a luxury. I would almost say it's like, it's literally being used. Like the DeepMind paper is like the perfect example of that. This is like an actual production use case where they decided that like, hey, rendering the nerf is easier and it's going to be more photorealistic than getting some 3D artists to like recreate the inside of our lab, right? That's what this paper here is showing you. It's like, hey, recreating this entire fucking scene with these like posters and this wooden table and like all this bullshit is really hard, but fucking just making a little splat way easier. So I think you're already seeing splats being used in robotics just because they're capable of achieving a higher rendering quality and a more realistic render than meshes and textures, and it's easier to create them than a full like scene, which you need to basically have a game developer and like know how to use Unity and Unreal and like create models and deal with all the light. Like there's so much shit that you need to do in order to create a realistic simulation using assets with meshes and textures compared to Splat. So I think we're already seeing that even though they're still kind of in the early days, splats have a use in robotics, and I think it's only going to get more and more obvious, especially now that you have, for example, this GSplat project, right, where you have a nice, clean, open source implementation that you can use, right, and you have companies like Luma, right, which make it very easy. All you got to do is go on their website, you upload a bunch of images, and they'll give you the splat, right? So I think as the tooling around splats gets better and better, I think that it's a no-brainer for robotics. Which version of GS to use when working with high-quality images? I mean, I think if you want the highest possible quality, I would just go to like a startup, like a Luma AI, something like that. Like they have probably the best implementations, but if you really want to do something open source, like you can use this one. When will we see the first GPUs with integrated Gaussian splatting ASICs? I mean, you could say that literally that's already the case, right? Like, what is a GPU? A GPU is a ASIC or an application-specific integrated circuit for rendering, right? So, like, GPUs were designed to render shit. That's what they're designed to do, right? They're specific for that use case. And then we only then later figured out that they could be used for machine learning and pushing gradients. And again, only later did we realize that, hey, they actually work very well for Gaussian splats too. So I think ASIC, calling a GPU a Gaussian splat ASIC is a little bit rich, because whenever they were originally designed, they weren't like designed for Gaussian splats, but it's pretty close to something that would be designed for Gaussian splats. So is there going to be specific GPUs that are like even more application specific for Gaussian splats? Maybe I could see a situation where the VR headsets of the future, right? Like the Pico headset that they have here, maybe like imagine like a Meta Quest 7, you know, once you get to a point where everything is a Gaussian splat, all the volumetric videos are Gaussian splats, all the video games are Gaussian splats. So once Gaussian splats kind of subsume the entire like representation space, then yeah, maybe I could see VR headsets that have like effectively like a little chip in there that's specific to Gaussian splats. But right now, that's not the case, right? The little snapdragons inside these VR headsets are more being optimized for physically based rendering. How is the idea behind converting to images to Gaussian splats? So you use the images to create the splat, right? So like ultimately, when you are taking these images, right, with your cell phone, what you're doing is you're collecting an image that you're going to use here to compare to the image that gets rendered, right? So like the GSplat is really just these variables here, right? It's these variables, and you have these variables for every single one of your splats, right? So if you have 110,000 splats in a scene, ultimately what you're doing when you're training a splat is just changing the values of these, right? So slowly over time, you're pushing gradients to change those. And where is that gradient coming from? That gradient is coming from the images that you recorded, right? So you recorded some images with your iPhone camera, and those are basically being fed up here, and they're being used along with the images that are rendered from your current Gaussian splat. You look at the difference between those, and then that is your loss function, and that allows you to push a gradient all the way back and adapt these. And then once you adapt these, then the next image that you create is going to be slightly better and closer to the image that you captured. So that's the basic process of how the images that you capture are being converted into Gaussian splats, which are this right here, these numbers or these parameters. Visualization for humans as a barrier. Computed math space volume solution set should be what we aim for. I'm not 100% sure what you mean there, Aries, but yeah, I feel like even for something like the 1x world model, let's look at that 1x world model. Yeah, as far as I understand, this is just straight to pixels, right? It's not, there's no 3D underneath this. Is there a 3D representation here, or is it just all 2D? Let's see, Control F, 3D. There's no 3D. 2D. Image. Yeah, so you see here how they say image sequence, right? So the input into this world model is a sequence of two-dimensional images, and then the output of the world model is basically another two-dimensional image, right? So there's a fundamental problem there, and the fundamental problem is that the real world is 3D, right? Like, I feel like an actual real robotics world model should have like an underlying 3D primitive, like a Gaussian splat. You know, I think these two-dimensional, it's just not the right representation, right? A two-dimensional image is kind of like a weird lower dimensional projection of a real underlying 3D scene. So obviously these guys are using image sequences because they're probably using a pre-trained diffusion model to generate the images, right? Like all the generative 2D stuff is way better than the generative 3D stuff. But I feel like once Gaussian splats get good enough, I feel like the fact that they're a real 3D representation, right? It's like actually 3D at its core. That's going to make it a fundamentally better way to create robotics world models than what they're doing here, which is just basically image sequences, which is like 2D frame, 2D frame, 2D frame, 2D frame, and then you predict another 2D frame, right? I think if I think about the future, I feel like it has to be a 3D representation at the core. It can't just be these two-dimensional images. Would I do a stream on how to incorporate physics into splats? Yeah, I think there has been some papers. There was like what was it called? It's called like bouncy splats. Bouncy splats. Bouncy splats Gaussian. Yeah, these ones. This was pretty cool. So this is like a paper where they have physics properties in Gaussian splats, and you end up getting these kind of like, maybe it's not this one. There was like a paper I remember seeing where you can actually interact with the Gaussian splats, and there was like a bounciness to it. I'm never going to find this fucking paper, but yeah, we'll read it. You know, this isn't the last time we'll look at Gaussian splats. Probably in another couple months, I'll do the same thing, and I'll go on this guy's page and I'll scroll through. I'll find like 10 other Gaussian papers, and I think at that point we'll have more kind of physicsy based papers, and then we'll see where it's at. So I don't know. I like to check in on different research areas and see where people are making progress. All right, guys. I have to head out, so I'm going to end it there. Thanks for hanging out. Thanks, Aries, Swati B, Patrick, Sheb, Tomcat, Kiko Band, Sarah, Snook, Sleepyhead, Majetti, Frigo, Brian, Patrick, Trust Me Bro, Oma Viva, Joss. Thanks, everybody, for listening. Hope you got something out of it. If not, have a great weekend, and see you guys later.